Hey everybody, we're going to talk about KSP in this video here today. And so KSP is very similar to KEQ in the sense that what it is a big K with the little sp. And so the way that it's named is the constant of the solubility product, or the solubility product constant. And what this does is this gives us an ability to predict how soluble something will be once something really reaches what's called a saturated solution, or we could say that that term is also when it reaches equilibrium. And so typical questions that you'll get will look like this. The KSP for MgCO3 at 25 degrees Celsius is 2.0 times 10 to the minus 8. What are the ion concentrations in a saturated solution at this temperature? And so what you want to do with these particular questions is you want to be able to write a dissociation equation. So if we have MgCO3, and that will be solid, we want to write the dissociation equation for that when it actually dissolves. And so MgCO3 reacts to produce Mg2 plus and CO3 2 minus. And so the KSP equation is the exact same as what our KEQ equation was, where we have the concentration of the products over top of the reactants. But with KSP, one of the beauty things is, remember, we don't want to include solids in any constant expression, and we will always have a solid on the left side of our reactants. And so what we end up with this equation for our KSP will be the Mg2 plus, which would be aqueous, and the CO3 2 minus, which would also be aqueous. So CO3 2 minus, which is also aqueous. And we don't actually have any reactants to include because this MgCO3 is a solid. So we could say that this reaction is basically over 1. And so what we have then here is a scenario where we have some X amount here, some X amount here. We don't know what those concentrations are, but we do know the KSP is 2.0 times 10 to the negative 8. And we don't know what this one is, and we don't know what this one is. So we end up with 2.0 times 10 to the minus 8 is equal to x squared. Now what we can do with this question is take the square root of both sides, and that'll give us the final solution for what x is. So 2 times 10 to the negative 8, and we want to take the square root of 2 times 10 to the negative 8. We get a value of x equal to 0.000141, or 1.41 times 10 to the power of negative 4, and that will be a molarity because we're dealing with a concentration. And so that is how you can use KSP there to calculate different values. When we get into a question like this, calculate the molar concentrations for silver chromate in a saturated solution at 25 degrees Celsius. So we would need to go to our data table. We would need to look up what silver chromate is. Silver is all the way down here, Ag+. Chromate is over on this left side, CrO4 2 minus. And so when we go to our KSP, we will have Ag2CrO4 like this, and then that would be a solid. We'd write the dissociation equations, Ag+ plus CrO4 2 minus, and both of those would be aqueous. It's like taking salt and putting it in a solution of water. It's going to break up from NaCl, which is table salt, into Na plus and Cl minus. Now the problem with these questions here is now we have a balancing coefficient because we have an Ag2 and we have 2 Ag pluses. So now when we solve for KSP, we're going to have the concentration of Ag squared, and we're also going to have the concentration of CrO4, and that one doesn't need to be squared. Now it's also worth noting, if you remember our icebox questions, we assigned x values to say, hey, this is how much it will change. And what we had assigned was that this x value, because this is a balancing coefficient of 1, will just be x, and this one would be 2x. So now when we rewrite this KSP expression, we need to write it as 2x squared, and we need to write this one as just x. And so now we can start to fill in that KSP number where we had 1.1 times 10 to the power of negative 12 is equal to 2x squared. This 2 needs to apply to both the 2 and the x, so we end up with 4x squared, and we would multiply that by x. So 1.1 times 10 to the minus 12 is then equal to 4x cubed. To solve this, we'd want to divide by 4 first. So 1.1 times 10 to the power of negative 12 divided by 4 gives us 2.75 times 10 to the minus 13, and that's equal to x cubed. And so we'd want to take the cube root of both of these sides. So we'll take the cube root of both of these sides, and you end up with an answer where x is equal to 0.0000650, or 6.50 times 10 to the power of minus 5 molarity is equal to x. And so what we could do then is I'm just going to bump all of this content down a little bit so that we have a bit more room to work with. So we'll bump all of this down just a smidge here. We knew that our x value was 6 times 10, 6.5 times 10 to the minus 5, 6.5 times 10 to the minus 5. And so we know that this one here will be 6.5 times 10 to the minus 5. But what we need to do for the other one, what we need to do for that left answer there, is we need to multiply 6.5 by 2. So when we multiply that by 2, we get 0.00013, or 1.3 times 10 to the minus 4 molarity as our final solution. And so where these questions get a little bit more hazy is when we start dealing with multiple exponents or balancing coefficients present in these questions. But for the most part, they're fairly straightforward as we plug in an x value for these numbers and say that we don't know what those concentrations are. So that is how you can calculate KSP. KSP again tells us how soluble something will be, or how much of something we'll have once something reaches a saturated solution or when it reaches equilibrium.